we got into all kinds of trouble with the derivation of the Verlinde formula. I looked up the Verlinde digraph paper that had the same derivation, and I realized that what the yellow book has done is print the paper word for word. Okay, I mean, same equation, same line, same explanation. So, okay, so I will come back after consulting some experts about this derivation. At the moment, let's put it on hold. Okay, I don't understand all the various things that they dropped at various stages. I don't understand why. I will find out. That's clearly a good reason, because the formula is clearly correct. I will find.
Verlinde in his Jones paper.
Verlinde. Okay. So now there are independent proofs in Chern-Simons theorem. Okay, and that is a simpler and more physical proof. But the original Verlinde formula proof claimed to be correct for every rational conformal field theorem. So was not allowing you to go to 3 dimensions, use these Wilson lines, and so on. And I will go through all that when we discuss Wessel-Minowitten theorem. I will go through these more physical and nicer, to my taste, nicer ways of functioning. But at the moment, we've not even studied Chern-Simons theory, right? So we don't want to go that way, right? But in fact, so that takes me. So once I get enlightenment on this proof, this pentagon identity proof of the Verlinde formula, once I understand it, perhaps, okay, I'll consult either Ashok or Sunil. One of the two of them will know. Okay, so they were around when it was happening, and they were both conformal field theory people, so they will have understood it and have an opinion on it. I'll consult them and I'll get back to you guys. Okay, but for now we just start the third part of our course. Yes.
Abhijit wrote this paper in search of CFTs.
I remember that, yes.
Yeah, and there also he was talking about these pentagon diagrams and trying to solve the...
Pentagon, he was trying to solve crossing, right?
Yeah, then it turns out to be just solving pentagon diagrams.
Oh, I don't even remember that, okay.
So I just wanted to ask that whether Verlinde-like thing is... this is all just preference.
Okay, no clue. Yeah, his paper, maybe are we talking about the same paper, the one where he does just group theory, SU2 group theory?
He says that solving the crossing equation, any d-dimensional CFT is same as solving this certain kind of group theory problem.
Yes, group theory problem. Now, in group theory, there's no analog of the Verlinde formula, right? Because there's no analog of the S matrix. So I'm not completely sure whether there'll be an analog, in that situation. Okay, but my proposal is that we now start the third part of our course. Okay, so the first part was general stuff. The second part, roughly speaking, was minimal models. And the third part is going to be about current algebras. Okay, so let's start that discussion. Okay, you might remember that at the beginning of the course, we started by studying the OP. Okay, and we had on very general grounds argued that this OP had to take the form C by 12, I don't know, something by z to the 4 plus 2t of 0 by z squared plus del t by z. On very general grounds, we made this argument. Okay, and all that we really needed to make this argument was to know how T transformed under global SL2R transformations. That fixed the last two terms in the algebra. In fact, the last term was just how it transformed under translations. Okay, the second term was under the scalings. Okay, and then the other thing that we needed to know was that this was a dimension 2 operator, and that there were no, in a unitary theory, there were no operators of dimension less than 0. Okay, so this was an algebra of spin 2 holomorphic currents. Now you might ask the following question. 2 is a nice integer, it's a small integer, but there's another small integer that's smaller than 2, it's namely 1. And you might ask, is there a theory of interest? Can there be theories of interest which have spin 1 holomorphic currents? Okay, we will see even by the end of this class that there are several. Okay, and in that situation, the question we're going to pose ourselves, we're going to ask ourselves is the following. Okay, what can we say about the OP of the various spin 1 currents with themselves? Spin 1 holomorphic currents. Okay. What? Del X is an example, exactly. That's an example. And, okay, good. That's an example. Or if you have a free fermion, then psi bar psi is another example. Okay. But we will see more interesting examples as we go. Okay. Excellent. So what we're going to do for 2 minutes is some very abstract analysis. We're going to say, suppose the theory, wherever it is, has a bunch of spin 1 currents that we call JA of Z. I think, let's put it down. Okay, this is some spin 1 holomorphic current. Okay, now what we're going to ask is, what is the OP? What form can JA of Z, JB of Z take? JB of 0 take. Okay, excellent. Now, the first thing to say is the following. If these currents are all mutually local with respect to each other, so they're all operators in the same theory, okay, the OP has to appear with integer dimensions. You can't have fractional dimensions because then that is non-local, it's not well defined. Okay, so, and once again, let's assume we are in a unitary theory. So the lowest dimension operator is the identity. So identity can appear. Spin 1, dimension 1 operators can appear. Dimension 2 and higher can appear. Okay? So in this thing, we could have, let's say something like KAB over Z square. Okay, we could have that. We could have plus FABC JC over Z by Z. Why? Yes.
Since we're using unitarity, since we derived this TTOP assuming unitarity,
Yes.
if we considered a non-unitary theory,
Yeah. Yeah. You know, there is probably a better another derivation that does not use unitarity. It's somehow something about the symmetry algebra. It's a good question. It's a good question. We should have better derivations, one that does not assume unitarity for the TTOP. Because, for instance, in the minimal models that were non-unitary, we still had the same algebra. I think it has to do somehow with, one way of thinking of this TTOP, one way that mathematicians like is the following. They write down the algebra of diffeomorphisms. Okay, that's just the algebra that you get from Virasoro minus the central charge. And then they ask, what are the possible central extensions of this algebra? And then they classify this as the Virasoro algebra as the only possible consistent central extension of this algebra. Okay, and then that you can then back calculate and give the TTOP that we got. Okay, so this would be one style. This is, if a mathematician were giving this course, I think this is how they would present it. This would be a group theory style of deriving that, and that makes no use of unitarity. Okay, similarly here actually, we're going to get out of this the Kac-Moody algebra. Once again, mathematicians have classified extensions of, as we will see. So once again, what I say will actually be true even without unitarity. Much of what I say will be true without unitarity. But I'm motivating it in unitary theories, because that's usually where we would want to be. Okay?
another thing.
Yes, but excellent question. Yeah.
If we have a spin, stress and tension are theory,
Yes.
spin to operator,
Yes.
this means we are theory is local.
Yes.
Does locality imply unitarity?
No. Okay. So non-unitary minimal models are local.
So they.
Local, I don't know what you mean by local, but certainly they obey, the OP is local. Okay. Sometimes they have these negative dimension operators. In fact, they always have negative dimension operators, which means that correlation functions don't die off when you go to large distance. If you call that non-local, they don't obey cluster decomposition. Now, if that you may call non-local. So I don't know what your standards for locality are.
My locality standards, I don't know, but my standard was what people call this center charge going to zero, the free field theory.
Free.
Generalized free theory.
Generalized free field theories?
They are non-local.
Ah, because they don't have a stress tensor.
Yeah.
Okay, good. So the question you're asking is the following. You're asking, there is a Hamiltonian. All theories have a Hamiltonian, even your generalized. Question you're asking is that Hamiltonian the integral of a local current? Okay. I think that is the question you are asking. In generalized free field theories, the answer is no. Yeah, in all our theories, including minimal models, because there exists a stress tensor. And by that standard, it's local. Okay, excellent. Excellent. So let's keep going. Now, we've got these two tensors, and then plus regular, right? Okay? Now, we've got these two tensors in the game. Okay, KAB and FABC. Now, we can always choose bases so that KAB is diagonal, is diagonalized. Okay? So, let's choose such a basis, and then let's rescale our current so that all the diagonal values are the same. Okay? So we've got K times delta AB. The absolute normalization of these currents we've not yet determined. Okay? And that will come in a bit. Okay. We've got K times delta AB times FABC. Okay, and why, by the way, did I put JC on the second term? Because you see, the only term that could appear is a spin-1 holomorphic current, and we've assumed that these J's are the whole set of spin-1 holomorphic. Okay, so very simply, okay, very simply we've got this structure. Okay. Now, what do these FABCs mean? Okay, I've written this FABC. What does it mean? In order to understand that, let us do a mode expansion of J. Okay, JA of Z can be expanded in the usual way as JAM Z to the power M. Now, am I getting minus M? What? M plus 1, yeah, M plus 1. And, but is this M or minus M? Let's see. So, J minus M creates states. So, it's positive energy. So, that should be accompanied by Z to the power J minus M times Z to the power M. And so, this sounds good. Yeah. M is equal to 0 to infinity. And the plus 1, of course, reflected the fact that J was a dimension 1 current. Just like when we did T, we did M plus 2. Okay. Now, this guy, let's write the formula for these various JMs. Okay, the various JMs. So, JM is equal to Z to the power M, integral J of Z, and then 1 over 2 pi I. This is just the Cauchy theorem. Sorry, hardly teaching, unless it's important. I'm teaching, so if it's okay. Yeah. Okay. 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 So this is the formula for JM, very similar to the formula we had for LMs in terms of T. Okay? I want you to focus on J0 for a moment. J0 is equal to 1 over 2 pi I, integral J of Z. Now, integral of J of Z is just a charge, at least one part of the charge. Integral Jz plus integral Jz bar. Well, let's say that there's not even necessarily an anti-holomorphic current. Okay, so imagine that we make a current vector such that Jz is equal to Jza is equal to J, and Jz bar. Maybe I want this one to be upper. No, I want this to be lower. Yeah, and Jz bar is equal to 0. Okay? This is the definition of my two-dimensional current. Suppose for a moment. Okay? Then with respect to this two-dimensional current, the charge is just integral Jz dz. You remember we showed in general that the charge was integral Jz dz minus integral Jz bar dz bar on the unit circle. Okay? In this case, because Jz bar is 0, this charge is just integral Jz dz. Okay? So this quantity here, this J0, is the charge. Okay? Now, an interesting question is the following. What is the commutation relations of the charge with the various current operator? Okay, in what representation of the symmetry? Okay, so in particular, this quantity, this J, tells us that we're in a theory with symmetry, with a global symmetry. In fact, this global symmetry is now a huge symmetry because each of these JMs is conserved. JAMs is conserved. Just like each of the LMs. You know, there's a symmetry algebra involving each of the JMs. Okay? But the simple guy, just the ordinary vanilla symmetry, is generated by J0, the charge, integral J0. Okay? And that symmetry, okay, that symmetry, so there are two questions. Okay, so one question you can ask immediately is, what is the algebra? What is the algebra of these charges, JA zeros? Okay, what is J? How do I put it down? I'm sorry. A0, commutator JB0. Okay, maybe I should call this QA, QB. So I'm just defining JA0 as QA so that we don't have to write too many indices. Okay, but now you remember the general procedure to answer such questions. Exactly. The commutator was one contour integral and then another contour integral minus the reverse order. And then you took one guy around the other on a point and then integrated that, right? So I'll just draw that diagram to jog your memory. That there was this guy and this guy minus the second guy down here. Minus this guy and this guy. Okay, but what we did was to think of this as integral. First do, fix some point on this integral. Fix some point on the white curve. And then the difference between these became, around that point, this integral. And then we integrated that on the white curve. Okay, but that first circle, we could then get as the pole in the OP. Right? So if we wanted to do QA, QB, what we have to do is to look at the pole in the OP of JA of Z, JB of, let's say, W. Look at the pole in the OP, whatever's the residue of that pole, integrate that over this contour. That gives us the answer. Okay, now notice that in these zeros, in these charges, there are no extra factors of Z. We are doing JAM, there would be some extra factors of Z to the power M. But here there are no extra factors of Z. So the pole is what you see. The pole in the OP between these currents is just the pole in J's, which was this FABC. Okay, so what we get therefore is FABC JC of W integrated over W. I'm not keeping track of all the 2 pi's. That's easy to keep track of. You get it straight, right? Okay. In fact, the 2 pi's, because each J has has a 1 over 2 pi I. The whole thing comes with 1 over 2 pi i's, and then Cauchy's theorem gives you an extra 2 pi I up in the numerator, so it cancels out. Okay. So this is in fact equal to FABC QC. And so we come to the unsurprising conclusion that the global charges built out of these currents obey the commutation relations of an ordinary Lie algebra. Okay? So that the global charges of these currents obey the commutation relations of an ordinary Lie algebra. Excellent. So what we're dealing with now, we see, is some generalization of a Lie algebra. Okay? What we're dealing with is some generalization of a Lie algebra. Okay. So let's try to study understand this in a little more detail. So we've got JAJB, K delta AB by Z squared plus F ABC C of 0 Z plus dot dot dot. Okay, so we've got this Lie algebra, but now we've got a larger symmetry, larger algebra, an infinite dimensional algebra involving all the JAMs. Let's compute that immediately. Okay, so how does our algebra go? Once again, we just do the same thing. So we have commutation relation of JAM with JAN is equal to residue of the pole in Z to the power M, W to the power N. Well, let's say Z to the power M, W to the power N, and then we get K by Z minus W, the whole thing square, plus delta AB, plus FABC JC of W by Z. And the pole we're interested in is the pole when Z goes to W. Right? So this guy is really easy because it already has a pole. Any Taylor expansion of the Z, this was actually W, sorry, Z minus W. Right? We're expanding around Z, with Taylor expanding in Z around W. This already had a pole. Any further Taylor expansion here will make it regular. So we just said Z equals W. So the second term is W to the power M plus N FABC JC integrated over W. Okay, and this was equal to, that's this term, which was equal to FABC JC M plus N. Right, that was really easy. But what about this term? This term is like the central extension. This term is like the central extension of the Virasoro algebra. It's going to give us something else. What will it give us? Well, for this term, we need to Taylor expand this guy once so that we get a pole. Okay? So for this term, we get K, then M, then W to the power M plus N minus 1, and then no J. Okay? Now, okay, so this dW. But this is simply equal to K times M times delta of M plus N. Okay, I'm not keeping track of the 2 pi i's, but it's trivial to do so. You see this. Okay? And so we see that the generalization of Lie algebra is this infinite dimensional symmetry current whose algebra is JAM, JAN, is equal to FABC, well, let's write the central term first, K times delta AB times delta M plus N 0. Right. Okay, plus FABC JC comma M plus N. Okay, this infinite dimensional algebra based on a Lie algebra. Okay, the data that goes into this algebra is two things: the structure constants of the Lie algebra and this integer k. Okay, the structure constants of the Lie algebra and this integer k. Okay. Well, oh, in general, not an integer. We will soon argue in unitary theories it is, and this number k. Okay, k is called the level of the algebra. Okay, its name. Okay, M. Thank you. Thank you. K is called the level of the algebra, and FABCs are the structure constants. Okay, excellent, excellent. I now want to argue, okay, okay, that that this quantity k is necessarily an integer. Okay? Why do we expect that it should be an integer before? Well, I'm not sure, but one way you might, you see, once you try to write down Lagrangians for these theories, that becomes really clear. Okay, let me undertake a little diversion to answer that question. Okay. The question was, why should we expect you see, you can absorb k into the normalization of j, but then that changes the normalization of f. Yeah. Okay, so if you choose a canonical normalization for f, let's say I choose for SU2, the usual FABCs, epsilons, yes, then k has meaning. Yes. Okay, so that's what I really mean. That I choose a canonical normalization, let's say for SU2, then k is meaningful, and yeah. In fact, when we go through this a little more systematically, we will be very careful about these kind of things. What is actually the integer? And so on. But right now, we're just taking the first pass. Okay. Excellent. 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 So let me come back to exactly this question. The question is, why at all should we expect k to be an integer? Well, the whole study of these Kac-Moody algebras entered physics in some sense through this paper of Witten called non-abelian bosonization in 1984. Okay, it's a totally brilliant paper, totally brilliant physics paper. You know, it's a completely amazing paper. Let me tell you a little bit about it. That will give you a physics sense for why you expect k to be an integer. Okay. Witten started his discussion by asking, can I make conformal field theories of bosonic fields with SUN symmetry? Or maybe UN symmetry. Yeah, let's say SUN symmetry. Okay? Actually, it's very easy to make conformal field theories of fermionic fields with SUN symmetry. Just take n complex free fermions. Okay, that is SUN symmetry. Okay, yeah, so what? Okay, the question he posed was, can I make theories with bosonic fields that have SUN symmetry? He wanted to think of this as a non-abelian version of bosonization. You remember that a single free fermion, single free Dirac fermion, is the same as a single scalar field. So he asked, well, okay, of course, two Dirac fermions is two free scalar fields. That is true, but the two Dirac fermions have an SU2 symmetry, rotating them, whereas the two scalars, you lose that SU2. At most, you have an O2 symmetry, right? Because the scalars were real, not complex. So is there something I can do to bosonize the theory? Okay, retaining the manifest SUN symmetry in bosonic language. That is this question.
But
Okay.
one example of a CFT will bosonic CFT with SUN won't it be ON vector models or UN vector models? Excellent question. The point is that these ON vector models in the free point side. Sorry. Hello. Hi.
This is Neha.
Hi, Neha. Are you in TIFR?
I am. I just
Uh-huh.
and I was wondering how to find you.
Okay, I'm in A316, but I'm teaching a class at the moment. Would you be free around 1 o'clock, say?
I have to head to IIT Bombay actually.
Ah,
Meeting with the director there.
oh, I'm sorry about that. I'm middle of a class, so yeah. Okay,
Fine, that's fine. Go back to your class. Sorry, I didn't mean to disturb you. I will catch up with you.
perfect.
We'll talk
Okay,
later.
okay, thank you. Yeah, no, thank you. Bye. Okay, excellent. Oh, sorry about that. Your question was, what about just free bosons? Yeah, free bosons would do it, but they would have twice the central charge. You know, what you would do is to have n free complex bosons. And that central charge will be 2n. Whereas for the fermionic theory, the central charge is n. No? So while it would do it, it will not be the bosonization of your fermionic theory. It's got more than you need. What he wanted was a theory of bosons that was purely current algebra. I'll say the words and then we'll explain that as we go along. What he wanted was a theory of bosons whose Sugawara construction gave the stress tensor. As we will understand this as we go along, but since the question has come up. You know, there is a tight relationship between these J's and the stress tensor. Out of these J's, we can make an object that has the commutation relations of a stress tensor. We will go through that, perhaps in this class, perhaps in the next one. Okay? Now, but of course, you could have a theory which has J's, and let's say a decoupled sector. So the full stress tensor of the theory would be that part that comes from the Sugawara construction made out of the J's, plus maybe in general something else. Very special theories are those whose full stress tensor is just that you make out of the J's. That is basically telling you that in these theories, there's nothing more than what comes from the currents. It's not the currents are part of the theory. The currents make up the theory. Okay? So that's what Witten was searching for, a theory like that. A theory whose currents completely exhaust the stress tensor. What that means, I will have to explain to you. I will have to show you this construction. So. Okay? But that's what he was after. Is this clear? Okay?
When you were talking about C equals 180, then there was, I think, a theory at self-dual radius, I guess.
Exactly. The self-dual radius had k equals 1.
Yeah.
Exactly.
In that case, they were asking that the stress tensor was.
Yes, it was. Because in that case, you remember that theory was dual to the fermion.
Yeah.
Was just dual to one fermion. So that's the template in our mind. We know that the boson at self-dual radius is one fermion. What is the boson at, what is the theory dual to? Two fermions. Well, you could say two bosons at self-dual radius, but that moles the symmetry is not manifest. We want some bosonic description which makes the symmetry manifest. Okay? Excellent. So, now, let's say I want to keep SUN symmetry manifest. One obvious way to do this, okay? One obvious way to do this would be to write down a sigma model on the group manifold of SUN. Okay? So what do I mean by that? Okay. So what do I mean by that? Okay. Consider this Lagrangian del mu G inverse trace. Okay. So G is a matrix. It's some representation of the group. Let's say in the case of SU2, if you want to be as unabstract as possible, think SU2. But everything we're saying is SUN. Okay, so for SUN, G is an n cross n matrix and the defining representation of the group, let's say. Okay, so G is that matrix. You take del mu G inverse, D2x, okay, and you write down the Lagrangian, you write down this Lagrangian. So what is this theory? Your base is, as usual, the complex plane. But the target space is the group manifold. Is this clear? Now, let's look at the symmetries of this Lagrangian. Suppose I take G, okay, and let it go to G0 times G. Let me put the trace in here, okay, just to make it clearer. Suppose I take G and let it go to G0 times G. Then G inverse goes to G inverse G0 inverse. And then because of the trace, G0 is some constant to start with. Because of the trace, you cycle around. And it's invariant. Similarly, if I take G goes to G times G0. Okay, the G0 inverse is in the middle will cancel. Okay, so this Lagrangian, in fact, has invariance under G times G, SUN times SUN, which is what you wanted. Because these complex fermions, the holomorphic part of them have invariance under SUN, and the anti-holomorphic part of them have invariance under SUN. So the complex fermions had SUN times SUN invariance. Okay, so this is looking promising. It's a Lagrangian at least, which has the right symmetry structure. But now you can ask, is this theory, this is a Lagrangian, is this theory a conformal field theory? Okay, does this action define a conformal field theory? You see, now this is the first time in our class in which we are looking at non-free theories from the point of view of an action. We studied non-free theories, minimal models, but in this highly abstract way. Maybe we did a little action analysis when we talked about this Landau-Ginzburg. But that was, at the level of hand-waving. Okay, we never did any calculation using the Landau-Ginzburg picture. Okay, now you can, but now we're taking a more traditional quantum field theory point of view. Write down an action, this defines our theory. Okay, we want to understand its physics. Okay, okay, that's great. So, let us for a moment specialize to the case G is equal to SU2. In this case, the group manifold is a 3-sphere. Okay, and this action is a sophisticated way of writing down the following Lagrangian. Where x mu and x nu are 3 coordinates, any 3 coordinates of the 3-sphere, and G is the metric of the 3-sphere. For instance, you can use your favorite coordinates, whatever you like to use, theta, phi, something else, psi. Okay? That and these are just the same thing, as you can easily convince yourself. It's just the sigma model with the round metric, where the most symmetric metric on the group manifold. Okay? So what we've got here is a sigma model in a non-flat space. Are the words sigma model clear? We don't want to not understand something because of terminology. Sigma model just means this. It means you have, for instance, when we're doing quantum mechanics without a potential, we often write down mx dot squared by 2. But suppose the particle is propagating not on a flat space, but on some curved space. We would write gij xi dot xj dot by 2, where gij is the metric of this. That, in the quantum mechanics language, that is called a sigma model. It has just motion, free motion of a particle, but in a curved space. That's what sigma model means. And here, this is the free motion of a string, if you will, in a curved space. Okay? So people call these things sigma models. That's all that it means. Okay, great. So what we've written down here is a sigma model on a particular curved space, namely the curved space being the sphere. Now, if we were 1940s physicists, we might have thought that this is good enough to define the quantum theory. But beyond the 1940s, or beyond 1930s maybe, you realize this is not good enough, right? Because quantum field theories, when you try to define them, often have divergences. And you have to deal with these divergences. And these divergences induce renormalization group flows. And the divergences induce renormalization group flows. And the renormalization endpoint of the renormalization group flows are what we call conformal field theory. So the thing we have to ask is, if we take this Lagrangian, is it at a fixed point of the renormalization? Okay? Now, let's think for a minute. In 2 dimensions, the field X has dimension 0. So, del X is naive dimension 2. Therefore, naively, any g mu nu times del x nu is marginal. So the set of all marginal operators are parametrized by metrics on your target space. Note, it's a highly infinite dimensional space. Actually, you can also get b mu nus at the target space. We come back to that. When you take antisymmetric, we come back to that. But let's first focus on the metrics. Okay? So the set of marginal operators is not 1 or 2 or 3, as we have in 4-dimensional field theories, but an infinite dimension. So renormalization group flow, when it happens on this infinite dimensional space. Okay, it takes one metric to another, because as you're familiar with the fact that RG flow RG in the sense of fixed point, the UV RG flow, the Kalan-Zebanzik kind of RG flow, happens on the space of marginal operators, also on the space of relevant operators, but we've not turned on any relevant operators. Let's say we work in dimensional regularization. We'll never turn on a relevant operator, because there's no mass scale in the problem. Okay, dimensional regularization has the mass scale mu, but it only comes logarithmically order by order and perturbation. Okay, so say we define this theory in dimensional regularization. The theory is classically relevant, can only turn on other classically relevant operators just by dimensional analysis. So the whole flow happens in the space of these classically marginal operators, which is the space of metrics. Okay, and 1 or 2 more things. We'll come back to that. But right now, focus on this. But this is an infinite dimensional space. So what is the structure of RG flows in on these 2-dimensional sigma models? Well, an RG flow is an equation that is d by d log lambda. Let's say we do flow towards the IR. Lambda, when I say d log lambda, I mean I'm flowing towards the IR of G mu is equal to something. Okay, that something has to be built out of G mu. Now, what can that something be? Suppose we did a field redefinition of x. X is some function of y's. How will that change the Lagrangian? Can somebody suggest? So I do f is some function of y's. I'll get a new Lagrangian now in terms of y's. That will have a new effective metric in terms of y's. Can you see that the metric will change exactly according to the laws of diffeomorphisms? Because del x mu will be del x mu by del y, partial derivative, times del y mu. And that's exactly how metric transforms. Okay? Therefore, field redefinitions of a path integral are just nothing. It's just a different choice of variables in which to do the integral. But field redefinitions change the metric the way a metric changes under coordinate transformations in target space. So doing a field redefinition is not doing anything. I've not changed the theory. What does this tell us? This tells us that the answer to these flow equations, have to be coordinate redefinition invariant in target space. But G mu transforms like a tensor. So whatever appears on the right hand side must also transform like a tensor. Okay? So when you calculate at one loop, now let's see, you're looking, suppose I wanted to calculate at one loop. I did a calculation at one loop, and I should put a, okay, 1 by 4 pi alpha prime. Okay, I do a calculation at one loop. You get alpha prime, because it's a loop counting parameter, times something. That sense, the total thing has to be dimensionless. So it should be two derivatives, because alpha prime is dimension -2. So you're looking for a tensor at one loop, a tensor which is two derivatives, and has a mu index. Can somebody suggest an answer? Richie. Okay. So what you're going to get when you do this computation at one loop, some number times r mu. Okay, not too hard to do this computation. Maybe as part of this course, certainly in my string theory course, I teach this calculation. Maybe as part of this course, we'll go through it at some point. Okay?
Normal coordinates and expand.
Gaussian normal coordinates expand, that kind of thing. Exactly. Okay? So when you do this calculation for any G mu, you get this answer. Now we can specialize to the particular G mu under consideration. A particular G mu in this SU2 example was a 3-sphere. But for a symmetric space like a 3-sphere, G mu, R mu is proportional to G mu. So what we get is some, in the end, at the end of this in fact, that you could have guessed by symmetry. Because you see, you started with a metric which had SU2 times SU2 symmetry. Then the right hand, but nothing you're doing breaks that symmetry. The renormalization doesn't break that symmetry. So the right hand side can only mix with other metrics with that symmetry. But this is the unique three-dimensional metric that has SU2 times SU2 symmetry. Okay, so you will not change the form of the metric. All you can do is change the radius of the sphere. All that renormalization group flow can do in the situation is change the radius of the sphere. Just by symmetry, you would have seen that. I've given you the more general argument, but if you weren't so sophisticated, you could have argued this just from symmetry. Okay? So so suppose you have got, so what you get in the end is this, that you've got a sphere of radius r, let's say, and d by d log lambda of r, which is the radius of the sphere. I'll call alpha the radius of the sphere. Okay, is equal to some number times alpha. Okay, and the key question is, what is the sign of them? Okay, now the sign of this number turns out to be negative. There's some numerical coefficient, you know that. There's an alpha prime, of course, but all of that goes into all this business. Alpha prime cancels something. But minus, the point is that dr by d log lambda is negative. That is, as you go towards the IR, the sphere starts shrinking. Now, a very large sphere is hard to distinguish from just flat three-dimensional space. So a very large sphere you should think of as a very weakly coupled theory, because it's very near to the free theory, namely sigma model in flat three-dimensional space. A very small sphere, on the other hand, is very different from a flat three-dimensional space. So what we see is that this theory is asymptotically free. That is, in the deep UV, it starts out with very weak coupling. And the deep IR, it goes to very strong coupling. Now, what happens to this theory as very strong coupling? Well, you might hope perhaps you get a conformal field theory with very strong coupling. You may think that's where I'm heading, but I'm not. Turns out this problem is not studied. The sigma model on S3 is a very well-studied problem. Okay. Sigma model on S3 is a very well-studied problem. And this sigma model becomes gapped in the IR. In fact, it behaves very much like QCD. QCD, you've got asymptotic freedom in the ultraviolet and a gap theory in the IR. Okay, so this theory looked very good, right, for a while. But classically looked very good. But quantum mechanically, when we looked at this theory, we found it's not so good anymore. It's not a conformal field theory. In fact, it gives you a gap theory in the IR. Though it took a little work and a little thinking to come to this conclusion. So you might think, if you were not Witten, you might think, okay, it's a good try, but it doesn't work. Okay? But since we are talking about the person who is Witten, he thought more. So Witten was not satisfied with this. This you could have done. Maybe the other thing you could have also done. In 1984, I mean, now everyone can do it. Okay. But Witten was not satisfied with this because he felt that it should be that there exists a bosonic dual with this enhanced symmetry. So this doesn't work. Is there anything else that might? Okay. Now, I've already argued that at the level of this two-derivative action, of marginal operators, the only metric that is SU2 times SU2 invariant. Let's focus on SU2 for a while, then we'll check this. The only metric that is SU2 times SU2 invariant is this one. Working in the land of sigma models sounds reasonable, because we're working, let's say, a large enough sphere where sigma model should be good. What's going on? Okay. Now, Witten began to think a little bit more. And though this is not how his paper is written, it happens, this is 1984, which is also when string theory is undergoing a reflowering. It's clear that that plays into the game. So let's go back to the sigma model language. Sorry, this is turning out to be a very long diversion, but maybe it's worth it. Okay. So let's go back to this sigma model language. Okay. In the sigma model, we wrote down G mu nu del alpha x mu del alpha x nu. But there is something else we could also write that's also two derivatives in x, which is plus epsilon alpha beta del alpha x mu del beta x nu times b mu nu, where b mu nu is some function of x, just like x, just like g was. But in order for this to be non-zero now, this b mu nu is antisymmetric. Okay? At just at the level of actions, writing down the most general two derivative action, nobody can stop you from doing this. Okay? Now this b mu nu in string theory plays an important role. It is the NS and S2 form field that exists in every string theory. It's as much, a field in the bulk as the metric is. Okay? So when writing down string theory sigma models, people often wrote this down. So why not here? Now, let's look at this b mu nu a little bit more. Suppose I choose b mu nu to be del mu a nu minus del nu a mu, where A is any vector field. Okay? The minus was needed because of the antisymmetry. Okay, so suppose I chose that. Then let's examine this quantity. Okay, this is epsilon alpha beta del alpha x mu del beta x nu, and then write this term, say del mu a nu. Okay, but let's put this guy and this guy together. This is the same as del alpha of epsilon alpha beta del beta x nu a nu. Why is that? You see, this term has two terms. One derivative acts on the x, but that's zero because this is antisymmetric and this derivatives are symmetric. The second derivative acts on A, but then by the chain rule, that's the same as this. Because A depends on alpha, on coordinates only because x depends on the coordinates. Okay? But that then is a total derivative. Adding a total derivative to an action, at least for most purposes, is a triviality. Okay? So you see that this B field, whatever it is a field that is only physical up to shifts by this form, sort. So that B should be regarded as the same field as B plus D. So clearly you see that wherever this B field is, it enjoys a gauge invariance in the bulk. Okay? And the gauge invariance under shifts of B goes to B plus D. Which tells you that the physical content on B is dB. It's very similar to the discussion of the electromagnetism, where A has an gauge invariance under A goes to A plus D phi. The physical content is an F. So we sometimes call this dBH when we study string theory. We sometimes call this dBH, and H is equal to dB is the physical content of the thing. Now, once you have this in your mind, suddenly something occurs to you. Look, why was an S3, why was a sigma model on S3 invariant under SU2 times SU2? Okay, there are many ways to look at it. One pedestrian way is S3 is a surface in R4. Embedding in an R4, it's clear that it's invariant under SO4, which is SU2 times SU2. This round S3 clearly had this SU2 times SU2 symmetry. We saw it in that complicated way. But in the case of SU2, it's very clear. Okay? And what was key was that it was round. Right? Anything that preserves the complete roundness of the 3-sphere will be invariant under SU2 times SU2. Okay? Great. So you can ask, is there another deformation of the action that preserves the roundness of the 3-sphere? Now, a 3-sphere, clearly if you turn on H, such that H is the volume form on the 3-sphere. H is a 3 form. H is a volume form on the 3-sphere, on the round 3-sphere, then that preserves the roundness of the 3-sphere. In the same way that a field strength that is volume F on a volume form on a 2-sphere preserves the rotational invariance of a 2-sphere. So in the case of SU2, there's a very simple thing to do. Turn on an H. That is, preserve the roundness of the 3-sphere. That preserves the same symmetry as before. Is this clear? Okay. So turning on an H, which is this round 3-sphere. So the idea is turn on H. Okay, in a round way. That's the second thing you can do. But, look, when you study fluxes on a 2-sphere, you know, you are aware that fluxes on a 2-sphere are necessarily quantized. Why is that? Okay? The argument, very naively, you might think fluxes on a 2-sphere are necessarily 0. Right? Because the flux on a 2-sphere, suppose I've got a 2-sphere. Suppose I've got a 2-sphere. I want to compute the flux on the 2-sphere. That is the same as computing, by Stokes' theorem, this little line integral. Make this line very small. That captures all of the flux around here. But now I can turn it around and compute the line integral here. And if it's non-singular, it's 0. So that's the argument that a flux in a 2-sphere is 0. And it's a wrong argument. It's a wrong argument because it assumes that every smooth gauge configuration, it's a wrong argument because it assumes that every smooth gauge configuration, okay, is also a smooth configuration of A. Because when you do this A dot dl, you say it's same here, and here you're assuming A is smooth everywhere. But that's not necessarily true, right? We know that gauge theories don't work that way. Gauge configurations are smooth if you can find one patch in which they're smooth, another overlapping patch in which they're smooth, and then there is a smooth gauge transformation between them on the overlap. Okay? Now, in the case of U1 theories, you choose one patch to include the North Pole and go a little bit under the equator. Choose a second patch to include the South Pole and go a little bit over the equator. The overlap region is this band. Okay? You want a gauge transformation on this band, but the gauge transformation is a U1 valued field. And a U1 valued field on a band can wind. So there are inequivalent topological classes of this gauge transformation. If this topological class is 0, then it's what's called a trivial bundle, which means that you didn't need to do it in patches. There was an A field everywhere. And the flux is 0. But if the winding number is non-zero, then there is an obstruction to doing one gauge field everywhere. The winding provides that obstruction. And indeed, that winding number measures the flux on the sphere. Why does it measure the flux on the sphere? Because you see, A dot dl this way captures the field strength this way in the gauge field appropriate to this patch. A dot dl that way captures the flux here in the gauge field appropriate to this patch. We should be summing the flux appropriate to this patch plus the flux appropriate to this patch. But these two A dot dl's, they differ by precisely the winding. Because A changes by A plus D phi, and then the d phi term differs precisely by the winding. So that this argument that I gave is wrong precisely by the winding. Right? This argument would, on the middle of the equator, would have been the argument that this thing captures the flux this way, but minus the flux this way. And so they add up to 0. And that is wrong precisely by this winding. So the total flux on the sphere is necessarily an integer which is given by the winding of this gauge transformation. Okay? In a very similar manner. Okay? In a very similar manner. Okay? In a very similar manner, the H fluxes on a 3-sphere are quantized. I will give you an argument for that in a minute. Okay? But first, let's get to the point. H fluxes on a 3-sphere are quantized. Okay? And therefore, this additional term that I can add in this problem, this H flux, is not a continuous number, but discrete. Okay? And Witten argued, and I'm trying to see whether, okay, let me just finish this argument. Let's make this an impromptu revision, review of Witten's paper. Witten argued that with any non-zero H flux, in fact, we get a conformal field. Okay? But because of that, you see that the theories that you get are discrete. The level there was the amount of H flux. That is one other way of understanding from this point of view why these levels were discrete. Now let me see if I can let me see if I can I have Whitman's paper here with me, so with the help of that, let me see if I can give you, so let's devote the rest of this lecture to completing our review of Whitman's paper. Okay, because anyway, it's nice and very physical, and I wanted at some point to talk about it, so why not today? Okay, so let me see if we can see a little bit more, to understand a little bit more why this H flux stops the renormalization flow, group flow. Well, the first argument that Witten gave in his paper was just a calculation. He computed the one-loop beta function, including also the contribution from the H flux, and found that while this guy tried to shrink it, while RG flow running tried to shrink it, the H flux tried to expand it out. This is, if you think about it, very reasonable. First, RG flow running can't change the value of the H flux because that's an integer. And an integer cannot run continuously. So you can only, once again, we've got an RG flow only for the radius. Okay? Now, if you think from the point of view of, again, I'm invoking a little space-time intuition. But in space-time, very roughly speaking, the RG flow equations are gradient flow. And the gradient, the thing that appears in the gradient flow is the space-time action of string theory. I said this just to say that there will be a term in this RG flow equation that comes by taking the gradient of the action of H flux, which is H mu nu alpha, H mu nu alpha. Now you see that this thing becomes very large if integral H is held fixed. Then integral H square becomes very large when the sphere becomes very small. Is this clear?
Integral H is fixed.
Integral H is fixed. Let's do it this way. Say the sphere has radius r. If the integral of H is fixed, then the local density of H is 1 over r cube, k by r cube. So that integral over r cube will give you k. But therefore, density square is k by r to the 6. Now you integrate that. That takes another r cube out. But there's k squared by r cube. That density really blows up. So the theory doesn't want this. The flux doesn't want to be squeezed into a very small volume. And that shows up in the RG flow equation. It pushes back. Okay? And because of that, it happens that the RG flow, the curvature wants to shrink this way. Flux wants to push it out. These two balance at some point. Okay? So the first argument Witten gave was just this calculation. At one loop, he did the calculation. Now, when is one loop accurate? You see, flux, the force of pushing out by flux is proportional to k, or k square. So, one loop is accurate when the sphere at the fixed point is not very curved, so it's near to free. But that will be accurate when the push out is very large. So when k is very large. Okay? So in the large k limit, Witten's computation, the one loop computation, was reliable. Okay, the curvature was very small. Two loop and so on was highly suppressed. Okay? In fact, he got k, I'll look it up. I've got his paper here with me. But it balanced out at radius which is proportional, I believe, to square root k. So I'll check that. Okay, maybe let's see if we can. One by r square, you would naively think that the curvature is 1 by r square. This h cube h square is 1 by r to the 6. I'm doing it locally. 1 by r to the 6. So it sounds like radius to the 4 is k square. So radius is square root k. Perfect. Do you get that? Okay, so that's the kind of the radius of order square root k. So when k is very large, the sphere is balanced out at a very large radius. And your computation is accurate. But Witten, and I know speaking for myself, I would have been very happy I would have published that. I've done a one loop calculation, it's reliable, great. But Witten was not satisfied. He wanted argument for exact for all k. And then he evoked this current algebra that we're starting to use in the following manner. Okay, so let me. Okay, but first thing you have to understand is this. We've already done something quite interesting. At large k, we found a conformal field theory that has exact SU2 times SU2 invariance. Okay? However, at large k, this was not what Witten wanted. Witten started out by trying to find the dual to free fermions. Let's say at SU2, what is the central charge of the free fermions that have SU2? 3 by half. What? Are you saying 6?
No, I'm saying
2. 2 complex fermions. 2 complex free fermions has SU2 invariance. Okay? So he wanted a theory with central charge 2. But at large k, this theory has what central charge? What? 3 bosons. So 3. Excellent. Right? Because it's near to a free theory of 3 bosons. So large k, this can't be the answer he wanted. So you might think that the opposite end, namely k equals 1, is furthest from being free fermions. You might think that that's where he will get the answer he wanted. And that's true. This theory at k equals 1 is the dual to free fermions. We're going to see this in many ways. Okay, so I said this all just to motivate the fact that Witten was not satisfied with the large k. He wanted exact analysis at finite values of k. Okay, excellent. Now let's try to understand one or two more things. Okay. Looking at the fermions had SU2 times SU2 invariance, but they had more. Why did they have more? So the fermions. Okay, since it's so easy for the fermions, I'll work out SUN times SUN. Okay, so suppose you have psi, these are complex fermions I, and psi bar I, right, left movers, right movers. Each of them are complex. Okay, so if you want, I can call this tilde. Let's say right movers are tilde. This is complex, this is complex. Okay? Now, the object psi I of z, psi tilde j of z, psi, no. Let's do this. Let's call this, psi, I have complex fermions, complex left-moving fermions. Let me do the following. Yeah, let me do this. Say I start with the real fermions. So I have 2 n real fermions. So I have psi 1. Oh, I could have been doing SON theory, but anyway, let's stick to SON. Psi 1 plus I psi 2. I'm never going to write down right moving for now. Just everything's left. Okay, this I call psi, and psi 1 minus I psi 2 I call psi bar. Psi 1, psi bar 1. And similarly, I define psi 2, psi bar 2, and so on. Okay, now I take psi I, psi bar j, this quantity, both left moving. This is a dimension 1 operator. Okay? And this just by using the free fermion correlators. Just by using free fermion correlators and big contractions, you can check very easily. So let's do that. So what is our so I take normal order of this. So suppose I try to construct Jij of z is equal to psi I of z, psi bar j of z. Normal order. Okay. Our OP is a psi I of z, psi bar j of w gives 1 over z minus w. Psi with psi is 0, psi bar with psi bar is 0. Is this clear? And delta I. So now let's look at the OP of psi ij of z, psi I prime j prime of w. Okay. So first we get a term where we contract everything. Okay. So we will get delta I j prime delta I prime j z minus w the whole thing square. Clear? Then we do the things where we contract pairwise. Okay? So we will get, so for instance, if we contract this, let's say we contract this I with this j prime, then we will get plus delta I j prime, delta I j prime, and then psi I prime of w and psi bar j of z by z minus w. Okay, and then there's one more term. Okay, plus delta I prime j psi I of z psi bar j prime of w by z minus w. Okay? And this, if you think about it, just gives you the Fijk of UN. Because the generators of UN are the ijth matrix element. Okay? And these are the various currents. So you see that what we get here is the Kac-Moody algebra, JA, JB, 1 Z minus W, the whole thing squared, plus FABC, JC. Is this clear? So these free fermions implemented the Kac-Moody algebra at level 1. Okay? I now want to try to motivate. Oh, we're running out of time. Let me go on 5 minutes. I now want to motivate to you that this level is, as I suggested before, the same as the number of units of flux in the. By the way, you notice that these free fermions, in this case, I could have done something cheap with the free fermions. I could have added a flavor index. Instead of using n complex fermions, I could have used mn complex fermions, where there was an additional flavor index that I don't count inside the SUN. Then do you see that the level would have become m? Because for each of these flavors would give us the same 1 over z minus n. Okay, so the free fermions were giving us level 1, 2, 3 to m. That's the first hint of integrality. But okay, that's free theories. Well, free theory is something's in integer where, even scaling dimensions of free theories are integers or half integers. Not very convincing. Okay? But now the bosonic side is much more convincing. Okay. So, but anyway, if you wanted the dual to this theory, you're looking for a bosonic theory that implements a k equals 1 Kac-Moody algebra. That is clear. Now, let us try to see what is the relationship. Let us try to see what is the relationship between number of units of flux in this k. Even roughly intuitively. Okay. So, in order to do that, let's work out the equation of motion. You see, the first thing that you want from your bosonic theory is that you have holomorphic and anti-holomorphic currents. Okay, that is the first thing that you want. Okay. It had better be that you had holomorphic and anti-holomorphic currents. What would be nice is that left multiplication by G naught would be holomorphic, and right multiplication would be anti-holomorphic. That would be sort of nice. Okay. Let's see how whether that's working. Okay, so let's first start without the H flux. Let's start with the theory which was del mu G inverse. Okay, and now what we do is to work out the equation of motion. Okay, we're not going to finish. Let me just say in words and then we can continue in the next class. What you do is if you work out the equation of motion for this action here, you find that it's not the case that you get that the currents for the two different charges are holomorphic and anti-holomorphic. Okay, you have current operators that are both holomorphic and anti. But if you add the H flux and if you put the relationship between k and the radius that is suggested by the one loop computation, then precisely for that you see that we get a new term from the current. Let's say we're using the Noether procedure, from the H flux. And precisely at that value of k, okay, the currents separate into holomorphic and anti-holomorphic. This is very strong evidence that this conformal field theory, at least at large K, where all these classical sort of semi-classical calculations are valid, that this conformal field theory is actually going to implement a current algebra. Now, once you have done this, you can use Poisson brackets, okay, to compute the level. You might think this is strange because Poisson brackets normally is classical. How will it know about a quantum deformation of the level? But in this theory, the quantum deformation comes from a classical term in the action, namely the H-flux. So the Poisson brackets themselves are good enough to see the K deformation of the algebra. So Witten did a careful computation at large K. All this is valid only at large K. He did a careful computation of the Poisson brackets at large K and showed that that you get on this theory a Kac-Moody algebra. First, it became holomorphic and anti-holomorphic. Second, he could compute the Kac-Moody algebra and check that the level at large K at least was actually K. Okay? Now you see that the quantization of K is the same as the quantization of flux. And K was just identified with the number of units of flux. Okay? Finally, what Witten did is the following. Given that, now he postulated that at every K, the theory implements current algebra at level K. Now, current algebra at level K equals 1 is so, by the way, once you make this postulate, you can check, I will show you all of this in there. But once you make this postulate, you can check that at K equals 1, there's this lovely formula for this Sugawara central charge. C is equal to, what is it? Okay, I'll probably remember it wrong. I'm mixing up between SO and SU. But okay, there is a formula for the Sugawara central charge of this theory. And you can check that when you set K equals 1, it gives you the central charge you expected. Namely 2, the one that would be due to the free formula. And then Witten used many of the things we will explore over the next few lectures of the course, namely the tightness of representation theory of this Sugawara construct, of the Kac-Moody algebra, to argue that these two theories were actually the same. The fact that you got K equals 1 Kac-Moody algebra in the theory was such a tight thing that it allowed him to show that this was exactly the same as the free formula theory. Okay, I know I've said more than I've demonstrated in this class. Well, this was just a response to your question. But where the quantization comes from. Quantization is intimately linked to quantization of fluxes in the space-time theory. That's roughly the intuition. And the central charge from a bosonic point of view is just some flux space-time. Okay, perhaps we stop this lecture here.
And the next class, what's the plan?
Yeah, the next we are planning over the next few classes to do a systematic study of theories with Kac-Moody symmetry.
So should we take a look at the non-abelian?
Yeah, great. Take a look at non-abelian bosonization. If you want, we can do a more serious discussion. Maybe we can complete the discussion of non-abelian bosonization first in the next class. And then I wanted to basically systematic. Actually, my plan for this class was to show you that K was quantized from unitarity. We didn't get there. I will do that kind of thing. But where we are heading in the end is to look at the Knizhnik-Gromolodchikov equation, to understand what conformal blocks of these theories are, to compute some of them, and to try to understand the solution of theories which have these Kac-Moody symmetries. I also wanted to talk about the relationship of these theories with Chern-Simons theory in 2+1 dimensions. So that's roughly the plan. I'll try my best to follow the yellow book where I can understand what the hell it's saying. Okay, but otherwise we'll just maneuver ourselves. So the yellow book has like 7-8 chapters on Kac-Moody symmetries. That's what I wanted to go through.
Here the statement, finally the statement is that the sigma model for SEN with flux K
Yeah.
is equal to NK fermions with
MK complex fermions.
MK complex fermions.
Yes. And the similar statement for SON. The sigma model for SON with K units of flux. To even define what I mean by K units of flux away from SO3. Okay. I will do that. But with an appropriate definition, K units of flux, sigma model of SON. Oh, good. Sorry. Let me back up. The first statement was that with 1 unit of flux was SUN with 1 unit of flux is N complex fermions. Now, no claim beyond that. Okay? It's not the claim that with M units of flux, it is M times N fermions. That is not being claimed. Okay? The reason for that is, you see, as is what I said, that if you look at the Sugawara central charge for M at level M, for SUN level M, that is much smaller than the central charge of Mn fermions. So that theory, the theory which is Mn fermions, does implement level M Kac-Moody algebra, SUN level M Kac-Moody algebra. But it's much more than that. And actually one way of seeing that it's much more than that is apart from, is that actually it implements a level 1 SUMN. So we chose to willfully be ignorant, focus only on a small part. Okay, so that will not be something nice like this. But with K, 1 unit of flux is the N fermions. Okay. And I will try to understand this derivation of this Verlinde formula as well. Come back. This is also part of this business where maybe it's a part of this course. I mean, depending on how long you guys put up with me. Another thing that I have never completely understood in myself is these papers of Seiberg and Moore. These papers on chiral algebras by Seiberg and Moore. I've never understood them. I've tried many times. I'm hoping this course will give me motivation to finally understand them. It's very similar to the spirit of those papers is very similar to the spirit of this derivation of this Verlinde algebra that we tried last class. So maybe at some point in this class we will come back to these chiral algebras abstractly, if I can get my head around. Motivations for understanding the chiral algebras? Well, you know, first in the special case of Chern-Simons theories, these things play a role, just conformal blocks which you can construct by winding Wilson lines, right? I find Chern-Simons theories very interesting. So I feel I should know everything around that study. That is partly my motivation. But it also seems very powerful. You know, Seiberg and Moore claim to have a classification of rational conformal field theories. Sounds like the kind of thing one should know.